I'll be walking you through the H55601 or modeling physics for OCR Physics A in the exam series of May 2024. Let's get started with our section A. Question number 1, which row in the table shows two equivalent physical quantities? So for the first one, it's 0 degrees Celsius or minus 273.15 kelvins, which is incorrect because we know that degree Celsius plus 273.15 is equal to kelvins, so that's out. For B, we are given 1 kilogram meters per second and then 1000 newtons seconds. So bear in mind newtons is, well, 1000 kilograms meters per second squared times by second, okay, which essentially cleans up to kilograms meters per second, okay, which is not the same as 1 kilo, okay, that because it's 1000, so that's out too. For C, we've got 10 kilowatts, so that's 10,000 watts, and this is 10,000 Newton meter. We know that watts is joules per second, and joules is kilograms meter squared per second squared, and then per second. So that's obviously going to give you kilograms meter squared second to the minus 3. Newtons, as we know, is kilograms meters per second squared, and if you times it by meter, you are going to get kilograms meter squared s to the minus 2. So those are also out, which gives us D as the answer, and it checks out because millipascals is just 0.001 pascals or newtons per meter square, because that is the unit of pressure, force divided by area, so D will be the answer. Question number 2, what are the SI base units of Boltzmann constant K? So for Boltzmann constant, according to our data booklet, it is given in joules per Kelvin. And as I've already mentioned, joules is in kilograms meter squared per second squared, and then times it by per Kelvin. That gives us C as the correct answer. Okay, question number 3 now. A rubber bung is attached to a string, and the bung is whirled around in a horizontal circle of radius r. The rotational period of the bung is t, and the tension in the string is kept constant as the bung is whirled around at different speeds. Okay, which relationship is correct for the whirling bung? We know that if you have circular motion and of radius r, and we know that the centripetal force will be equal to tension. Okay, so tension will be equal to mv squared over r. Therefore, mv squared is equal to tension times the radius. We also know that v is 2 pi r over t. From there, it becomes 2 pi squared, whole squared, times by r squared over t, which is basically, we know tension is constant, so I'm just going to call it proportional to r. That basically then cancels out one of the r's like that. Okay, and then also we know that 2 pi is also constant, m is a constant as well. All in all, that shows that r is proportional to t squared. So r is proportional to t squared, or in other words, B is correct, and so is D actually. So we've got 2 answers here, which is very unusual, but I'll definitely take it. Let's move on to the next question, which is to determine the acceleration of freefall, g. A ball is dropped from rest and from a point vertically above a light gate, The ball has a diameter of 5 centimeters and is dropped at time t equals 0. The light gate output shows that the ball passes through the gate between these two times. Okay, what is the value of g in meters per second squared from these measurements? We know it starts from rest when t is equal to 0, u is also equal to 0. And it covers a distance of 0.05 meters, which is the diameter of the ball. The time it takes to cover that distance is 0.04 seconds. So we can work out the average velocity with which it's moving through the light gate, and that would be just 0.05 over 0.04 seconds, which is 1.25 meters per second. Okay, now that's first thing. Now the second thing is that when it is going through a constant acceleration, the average velocity over a given time period, which is 0.04 seconds, will be equal to the instantaneous velocity at the midpoint of that time interval. The midpoint of that time interval will be 0.1 plus 0.14 divided by 2, and that would give me a value of 0.12 seconds. So this velocity of 1.25 meters per second is at the time interval, or at the midpoint of 0.12 seconds. That's point number 2. Point number 3, if we consider suvat from the beginning of this motion, we know that v is equal to u plus e, and v being 1.25, u being 0, plus g is what we're trying to find out, and t is the time interval from the beginning, which is t equals 0, and therefore 0.12 seconds is the time to be used. That will give me g as 1.25 over 0.12, and that gives me 10.4167 meters per second squared, or just C as the answer, rounded to 3 significant figures. So I hope that helps. Question number 5. A block of wood is floating in calm water. The density of the wood is 700 kilograms per meter cube, and that of water is 1000. What percentage of the volume of the block is above the waterline? So we know that the weight of the water displaced is equal to the weight of the block. Or we can also say that because the density of wood is 700 versus 1000, 70% of the wood is submerged. That is going to give me 30% as the answer, which is above the waterline. So A is the answer there. Question number 6. We are told that a horizontal uniform beam of length 4L and weight W is supported at both ends. An object weighing 2W is placed on the beam at a distance of L from one end. What are the magnitudes of the normal reactions N1 and N2 on the supports at the ends of the beam? We can deal with this question using two equations. One will be just based on the forces. W is going to act from the middle because the beam is uniform, and the total upward forces will be equal to the total downward forces because the resultant force is 0 as it's in equilibrium. So that means 3W is going to be equal to N1 plus N2. Then we can consider the moments. So I'm going to take moments about N2 because it's easier as the distance is from there. For that, I'm going to get 2W times L plus W times 2L, so 2LW, is equal to N1 times by 4L. And if I just cancel all the L's out, then I can say that 4W is equal to 4N, or simply N1 is equal to W. And if I use this into my equation above, okay, I can then say that 3W is equal to W plus N2, and then N2 is therefore 2W. So that means B is the answer. Question number 7. The graph shows a velocity time graph for a vehicle. At t equals 0, the driver observes an obstruction in the road, and a short time later the brakes are applied and the vehicle stops. The braking force remains constant. Okay, and we've been given the same. We've been given the situation is repeated, and this time the vehicle starts with twice the original velocity. All the other variables remain the same. The fact that the velocity is twice means that the thinking distance is also going to be doubled. V is proportional to thinking distance. The rest is going to stay the same because we're given that the braking force remains the same, which means the braking distance will also be the same. So out of these 4 graphs, we can safely say that the gradient in graph A is the same as the one shown in the diagram, whereas the rest of the other gradients are changing and the velocity is higher, so that initial thinking distance will also be twice as much. So A would be the answer here. Question number 8. The bob of a pendulum is displaced slightly so that the string forms a small angle of less than 10 degrees with a vertical. The tension in the string is T, and the small angle approximation applies. Which of the following pairs of quantities would give approximately within 2 significant figures the same value for the horizontal component of T? Okay, so first, let's split this up into the different components. Number 1, we will have W. We're going to have W, and there's going to be a vertical component acting against the W. Now, this will be theta. So this will be T cos theta, and we can also extend this line and we will have a horizontal component of T sine theta. We know that tan theta is approximately the same as sine theta for small angle approximations. So that means that T sine theta and T tan theta will be the same. C is the correct answer here. Okay. Question number 9. A mass suspended from a spring is pulled down 0.05 meters from the equilibrium point and is released. It oscillates in simple harmonic motion and the frequency of the motion is 2 Hz. At t equals 0, the mass passes through the equilibrium point. Okay, so we know that it is a sine graph. Okay, so it's either C or D. Now, what is the displacement in meters from the equilibrium at time t? Okay, so we know that x is equal to, therefore, a sine omega t. And we know that omega is 2 pi f. So frequency being 2 Hz, it will be a, which is, of course, 0.05 sine of 2 pi times 2, which is 4 pi, times t. So D is the answer. Question number 10. The natural frequency of an oscillator vibrating in air is 20 Hz. Which statement is correct about this oscillator? The natural period of the vibrating oscillator is 5 milliseconds. The time period is 1 over the frequency, and 1 over 20 does not give us 5 milliseconds. It's simply 0.05. So that's not going to be the correct answer. Be careful. They can easily catch you up in such questions. The oscillator can be forced to vibrate at a maximum amplitude at a frequency of about 20 hertz. Yes, so it will be resonance. Okay, so resonance occurs when the natural frequency is equal to the applied frequency or the forced frequency. And that is therefore the answer. Question number 11. Car drives over a bridge at a speed v. The path of the car is part of a vertical circle of radius r and the mass of the driver is m. At the top of the bridge, the driver of the car experiences apparent weightlessness and no normal contact force from the car seat. The acceleration of freefall is g. Which statement here is correct? So for this question, if we were to talk about a diagram, and let's say you are at the top of the circle, then the weight is acting downwards and the normal reaction force is acting upwards. And we know that for it to have circular motion, the resultant force is, of course, the centripetal force. So we can just set this up as W minus N is equal to mv squared over r. Now, for the person to experience apparent weightlessness, N has to be either 0 or, well, greater than 0. If we bring this down to 0, then W, which is mg, is equal to mv squared over r, and cancelling out the m will give me gr as equal to v squared. This will be the minimum velocity. And if the car's speed was greater than this value, it would experience apparent weightlessness. So the speed must either be equal to this or greater than that. So C would be the answer here. An object is released from rest and oscillates with simple harmonic motion. The maximum kinetic energy is U. The object is stopped and the process is repeated with the initial displacement doubled. What is the new maximum kinetic energy? So we know that Vmax is equal to omega A, where A is the amplitude. Now, if the amplitude or the initial displacement is increased, Vmax will also be doubled, okay? Which means that kinetic energy, which is half mv squared, will be quadrupled. So I'm going to say D as my answer. Question number 13. An object of mass 1 kilo is moving in a straight line at velocity of 10 meters per second. It collides with another identical object traveling at 10 meters per second in a straight line. Their initial velocities are perpendicular. The two objects stick together and we have to calculate the magnitude of the new combined velocity. Okay, quite a simple question, but first let's draw a little sketch of what's going on initially. Initially, we know that an object is traveling this way and another object is traveling this way, and they will collide with one another. Their initial momentum is just going to be the square root of the two momenta. Okay, so mass times velocity. So 10 squared and 10 squared. So that will give me 14.14 kilograms meters per second. Okay, so that's my initial momentum. Now, final momentum will also be the same, but now they have combined. Okay, so as to move together, because they've combined, their mass will be now 2. Okay, and let's call the velocity as v. Okay, so 14.14. And v is therefore going to be around 7.1 meters per second. So A will be the answer. Question number 14. At the surface of a planet with radius r, the magnitude of the gravitational field strength is g. What is the escape velocity from the surface of the planet? This is easy peasy. mgh, or in this case r, is equal to half mv squared. Cancel the m's out. V is equal to square root of 2gr. So our answer is going to be C. Question number 15. Stars rotate around the center of their galaxy. Observations suggest that the stars at the edge of the galaxies are moving at much higher velocities than expected. Well, that's dark matter, isn't it? B is the answer. So that's section A all done. Let's move on to section B. In question number 16, a car of weight 9,300 newtons is moving at speed v. The total resistive force F acts against the motion and is given by this formula, where K is a constant. The car is allowed to roll from rest down a slope of 5 degrees to the horizontal. The engine of the car is not switched on, and it reaches a maximum speed of 30 meters per second. And we've been asked to sketch a graph on the axis to show how the speed changes over time and add a suitable value to the vertical axis. So we know that it reaches a terminal speed of 30 meters per second, and it would basically accelerate until then. So we would have a maximum value of 30 right here, and it would basically be slow until it levels off. So that's part I done. For II, explain why the car reaches a maximum speed. That's because the faster it goes, the higher will be the resistive force. The resistive force is acting in the opposite direction to one of the components of the weight. If you just split the weight up into its horizontal and vertical components, this being 5 degrees, the resistive force F will be acting against W sine theta until the resultant force becomes 0. So the faster the car goes, the higher is F, which balances W sine theta and gives you the resultant force as equal to 0. For part II, we have to show that the value of K in the equation F equals kV squared is about 1. So for this, we know that the F, which is the resistive force, is kV squared, and this will equal W sine theta, because we know that F, or rather, I should say W sine theta minus kV squared is equal to the resultant force, and we know resultant force is 0. So therefore, we can work out the value of K using 9,300 newtons times sine 5 degrees divided by the value of the maximum speed, which is 30 squared, and that will give me 0.9 or 1. Part B, it says the car is now moving along a straight level track. The engine of the car delivers a maximum power of 75 kilowatts. Calculate the maximum speed of the car. So we know power is force times speed. And we know force is kV squared times by V. So V cube is power of 75,000 watts divided by the value of K, which is 0.9, and then we can cube root the answer and get 44 meters per second. For part C, it says changes are made to the engine so that it can produce double the original maximum power. Explain why the maximum speed of the modified car is not doubled. That is because power is proportional to V cubed. So doubling the power would mean that V will be equal to 2p cube rooted. So it's not going to be doubled. Question number 17. State Newton's second law of motion. It simply states that the resultant force is equal to the rate of change of momentum. Part B. A model of an aircraft is being tested in a wind tunnel, and the model is fixed in position by a support, and air is blown horizontally towards it by fans. In 1 second, 35 kg of air is moving at 50 meters per second as it hits the model. After flowing around the model, the airflow is diverted downwards at an angle of 30 degrees to the horizontal. The speed of the diverted airflow is still at 50 meters per second, and we have to calculate the horizontal and the vertical components of the velocity of the diverted airflow. So if this is the horizontal and it's diverted at 30 degrees below the horizontal, then it's going to have a horizontal component. The velocity will be v cos 30, or simply 50 cos 30, and that would be equal to 25 root 3 meters per second. And for the vertical component, it will be v sine 30, which will simply be equal to 50 times a half, or 25 meters per second. So for part II, we have to explain how the airflow around the model produces a force on the model. So since we know that there is a change in momentum due to the change in the direction of the airflow, the force on the air will be equal to the force on the aircraft. Due to the force exerted on the air, there would be a force exerted on the model. For the next part, we have to calculate the vertical lift force acting on the model due to the airflow around it. That would be simply equal to the change in momentum over change in time. The mass of the air per second is 35 kilograms. So m over delta t is equal to 35 kilograms per second. Therefore, the force will be equal to 35 times the change in velocity, which was 50 to begin with, but now it's going to be considering the vertical component, which is 25, so that will be minus 25, and that gives me 875 newtons of force acting in the vertical direction. Okay, question number 18. We've been given that mats made from rubber are often used in labs where heavy objects might be dropped. A rubber cord is tested to determine the material's mechanical characteristics, and the cord is suspended from a ceiling and masses can be attached to the free end. We've been given a diagram and a bunch of values where the height is from the ground. It starts with the objects already attached, and now one at a time you are removing the masses so that we can see that there is a drop in height. We have to complete the final column of the table, and that is simply the extension for the force of 6 newtons. That's the difference between the two heights, and that will be 0.54 meters. Next, we have to plot the data point for 6 newtons. If you have 0.5 right here, that will be 0.54 right here. Then draw and label two curves to show the loading and the unloading. So just watch out what the loading process is when the forces were added on and when the forces were removed. It starts off at 0 newtons of force and 0 meters of extension. At 1 Newton of force, the extension is 0.2. So that's going to be joined, and it will keep on going until that point. We are unloading it at 6 newtons, which follows the extension, and then it will be joined further. It doesn't go back to 0 extension, so we'll stop at 0.05. That will be the loading part, and this will be the unloading part. Okay, we have to discuss whether Hooke's law can be applied to the cord. No, because force is not proportional to the extension. As we can see, it's not a straight line. There is an area between the two curves that you have drawn on the graph. State the name of the derived SI unit of this area. The derived SI unit is energy, which, it's joules basically, as that's the energy. And so that will be my answer. For the next part, we have to explain the significance of this area to the planned use of the rubber. We know that the area under the loading is greater than the area under unloading. So that means that more energy is stored when heavy objects are used, and so when unloaded, they won't bounce as much. Part B. An alternative arrangement for the experiment is used. The arrangement makes it possible to cover a larger range of extensions. The cord is fixed to the ground. Describe 2 factors that would affect the accuracy of the results obtained using this alternative arrangement. So the first thing is the pulley, which may not be smooth, so friction would affect the extension, on top of the fact that the cord will have tension. And secondly, as H is larger, its measurement may not be accurate due to things like parallax error. Question number 19. Describe how to determine the wavelength of a monochromatic laser pointer using a diffraction grating. Explain how to analyze the measurements collected using a graphical method. Improve the accuracy of the measurements taken, and you are given the number of lines per millimeter for the diffraction grating. So let's get the diagram up first. In this diagram, we've got a laser pointer which is emitting a monochromatic light, which is passing through this diffraction grating with n number of lines per millimeter, and it's creating this diffraction pattern, producing the bright fringes at a distance of x meters away from each other. We know d, the distance between the diffraction grating and the white screen, is super helpful in measuring the value of theta, for instance. So let's first of all talk about what measurements we're going to take and how we can use those measurements to plot a graph. Then we'll talk about accuracy. Number one, we have to decide the formula that we are going to use. And we know that n lambda equals d sine theta. So we have to calculate the wavelength, and we can work around this formula by changing n and sine theta, and d is fixed. We know that d is 1 over n, where n is the number of lines per millimeter, so make sure we convert this into meters. If we end up, let's say, obtaining a graph of sine theta versus n, okay, where n is the number of the order of maximas, we would be able to get a straight line graph and we can work out the gradient if sine theta is on the y-axis and n is on the x-axis, then its gradient would be multiplied by d. We can then work out the value of lambda. Now let's talk about the measurements we have to consider. We would have to work out the value of sine theta. Now, what is theta? So theta is essentially the angle between the central maxima, so that is hitting straight across the screen, and the first order maxima. Let's say, for example, this is a first order maxima, and this is the central maxima, and this is the value of theta. Okay, so now in terms of Katoa, we know that this is d and this is x, which is the distance between the bright fringes. So technically tan theta is equal to x over d, but we know that theta is very small. Okay, so that means that tan theta can be approximated to sine theta. So that really helps, because if we can change the order of maxima, so if we go up to second order, our value of theta will change. So on and so forth, we can basically keep increasing the number of orders n and get a corresponding value of theta. We can measure that using a protractor to improve accuracy. One more thing about the accuracy is that d should be large enough to lower the percentage uncertainty in the angle. Secondly, we should also measure the x across either side. For example, I've got a central maxima over here, and this is the first order maxima right here. We can measure the x across both the central maxima and then half it. That would increase the accuracy in terms of the distance x, and thereby then increasing the accuracy in theta. So that's the second point I would like to mention. Finally, we should remove any ambient lighting by darkening the room, making sure that it's very clear to see the laser pointer emitting the light and creating the fringes. In terms of all the measurements such as d, I would use a meter ruler, and to measure theta, I would use the protractor, and also consider using SOHCAHTOA to make sure that the values are consistent with one another. So plotting the graph of the angle sine theta versus n would help me get the value of lambda. So I'm going to write this all down and put a link in the description box below so that you can see my work, my bullet points. So for now, let's move on to the next question. Question number 20. Define the internal energy of an ideal gas. It's simply equal to the sum of kinetic and the potential energies of all the particles. Part II. Use the formula below to show the average kinetic energy of a particle of an ideal gas is proportional to the absolute temperature of the gas. We know PV equals nKT, and PV is also equal to 1/3 nmc squared. Root means square speed. So we can equate them to one another, and we would notice n cancels out. So KT is equal to 1/3 of nmc squared. Now, if we want to introduce kinetic energy, that means we would have to essentially make half mc squared. That means we would have to times it by 2/3 in order to introduce that, because we have 1/3, because you can see that 2 and 2 will cancel out technically, mathematically, but it's essential to introduce that 2/3 because we want to rewrite half mc squared as kinetic energy. So there you go. Kinetic energy is therefore equal to 3/2 kT. Part B, we have been given the velocity of 4 gas particles at 290 kelvins in meters per second. Show that the RMS speed of the sample is about 430 meters per second. So all we got to do is square them, add them, and divide by 4. The answer that you get, you square root, and you would get 427 meters per second. Easy. Next, calculate the molar mass of the gas assuming an absolute temperature of 290 kelvins and RMS of 430. So we know in order to calculate the molar mass, we need to use half mc squared equals 3/2 kT, because that relates the mass with temperature and obviously RMS speed as well. So we've got m therefore equal to 3 times k, which is 1.38 times 10 to the minus 23, times t, which is 290, divided by the root mean square speed, which we calculated as 427. I'll use 430 meters per second, and that would give me a value of 6.49 times 10 to the minus 26 kilograms. And in order to work out the molar mass, it would just be times by the Avogadro's constant, which is 6.02 times 10 to the 23, and that would give me 0.039 kilograms per mole. Okay, part C. Spherical filament lamps are manufactured by a process where they're filled with a gas at 290 kelvins and low pressure. When the filament is switched on, the filament reaches a constant temperature of 2400 kelvins, and at this temperature the pressure inside is 120 kilopascals. Explain in terms of the energy transfers why the temperature of the filament does not increase beyond 2400 kelvins. You're not expected to refer to the electrical characteristics of the filament lamp. When the lamp is switched on, the electrical energy is converted into thermal energy, which causes the temperature to rise, which in turn increases the pressure of the gas. But since the volume is fixed, once all the gas reaches the same temperature, basically reaches a thermal equilibrium, and the temperature will no longer increase. Calculate the pressure of the gas within the filament lamp during manufacture. We know that PV equals nRT, and we also know that pressure is proportional to temperature. So we can rewrite P1 over T1 is equal to P2 over T2, as volume is fixed. Therefore, P1 is equal to the value of T1, which is 290, times by the pressure, which is 120 kilopascals, divided by temperature, which is 2400, which is the maximum temperature, and that value of pressure is 15 kilopascals. In question number 21, we are being given some information about relative intensities of different wavelengths from a star called Nu Persei. I think that's how you say it, but anyhow. So we've been given the surface temperature of the sun along with that as 5800 kelvins, and its wavelength at which maximum intensity is emitted is 500 nanometers. And the luminosity of Nu Persei is also given to us, and in the first part we have to use the diagram 21.1 to show that the surface temperature of Nu per se is about 6,300 kelvins. Let's break this down into some formulae and this diagram over here. Number one, we know the formula which relates the peak wavelength and the absolute temperature, and they are inversely proportional to one another. So using this law and this given diagram, plus this information about the sun, we can work a ratio out. So at 500 nanometers, the peak wavelength, let's say 500 nanometers, is somewhere here, the relative intensity, and the temperature at that wavelength is 5,800 kelvins for the sun. Now, if we have to show that the surface temperature of Nu per se is 6,300 kelvins, then that means we have to use a lower wavelength, because the wavelength and temperature are inversely proportional. So I can set this up into a relationship between the two, the sun and the Nu per se. I can say that the wavelength of Nu per se, I'm just going to call it NP, over the wavelength of the sun is equal to the surface temperature of the sun over the surface temperature of Nu per se. From here, I can rearrange this equation to work out the surface temperature of Nu per se, as it will be basically multiplied, so lambda s times by Ts divided by the wavelength of Nu per se. And now the question is which wavelength to use. It has to be less than 500 nanometers, and you have to do some trial and error over here and to see how far down can you go really to get that surface temperature of about 6,300 kelvins. I tried a few numbers for the wavelength. I started with 450 nanometers and I ended up getting 6,400 kelvins, so I knew I had to go slightly higher, and so then I used 460 nanometers of wavelength, and that gave me 6,304. So that worked out well. So I'm going to put those numbers in, as lambda s is 500 nanometers, and I do not need to convert anything because it's a proportion. Ts is 5,800 divided by the 460 nanometers, and that gave me an answer of 6,304 kelvins. Okay, that's part AI done. Now for the next question, we have to estimate the radius of Nu per se. We know the relationship between luminosity and the temperature is L equals 4 pi r squared sigma t to the power of 4. And we can rearrange this relationship and work out the radius quite straightforwardly, as we have been given all the numbers. So it will be 2.3 times 10 to the 29 watts divided by 4 pi, and that is Stevens constant, which is 5.67 times 10 to the minus 8. It's given to us. And t to the power of 4 is 6,300 to the power of 4. And all that will give me an answer of 1.4 times 10 to the 10 meters. Okie doke, let's move on to part B then. So it says electromagnetic radiation is collected from Nu per se by a sensor with an efficiency of 11% and a cross-sectional area of this much. The radiant power collected by the sensor is this much, and show that the radiant power per unit area arriving at the sensor is about this much. Okay, so we know that the intensity can be calculated quite straightforwardly We know it's power divided by the area, and that would be 7 times 10 to the minus 15 over 10 to the minus 4. And that would give me 7 times 10 to the minus 11 watts per meter squared. Now, incident intensity is therefore going to be, given that it's 11% efficient, incident intensity is going to be 7 times 10 to the minus 11 divided by 11%, or 0.11. And that gives me 6.4 times 10 to the minus 10 watts per meter squared. Part II. By the time electromagnetic radiation from Nu Persei reaches Earth, the radiation is evenly distributed over a spherical area with radius equal to the distance between Nu Persei and the Earth. Calculate the distance of Nu Persei from Earth in light years. Okie doke. We know the spherical area with radius r is equal to the distance between the two. The intensity we calculated, the incident intensity, will be equal to the power divided by the area. Area can be taken as a spherical area, so we know that 4 pi r squared is equal to p over I, and therefore r is equal to p over I times 4 pi, and then square root that. And again, it's a relatively straightforward question where you just have to be careful which intensity to use. So 6.4 times 10 to the minus 10, all square rooted, and that gives me 5.36 times 10 to the 18 meters. Now we have to convert this into light years, and we are given that 1 light year is equal to 9.5 times 10 to the 15 meters. And so if you divide this number by the number of meters here, we would end up getting 564 light years. Okay. Part C. The luminosity of Nu Persei was estimated using the temperature of Nu Persei and the HR diagram, where L is the luminosity of a star and L naught is the luminosity of the sun. So we've been given the two surface temperatures and the HR diagram, and we need to comment on the uncertainty in your value, calculated in part BII, of the distance of Nu Persei from Earth, and you may write on the diagram as a part of your answer. At the surface temperature of 6300 kelvins, along the y-axis, you could have a range of luminosities, right? So if you look, we have this section of the main sequence, which is therefore going to lead to an uncertainty. So Nu Persei could be anywhere on the main sequence along the y-axis for this 6300 kelvins of temperature. So therefore, uncertainty will be half the range. And since the radius is proportional to the square root of luminosity, the uncertainty in R is half the uncertainty in the luminosity. Question number 22. Satellite in a geostationary orbit around the Earth appears to remain at the same point in the sky when viewed from the ground. State one condition required for an orbit to be geostationary is that the time period has to be 24 hours. Calculate the orbital radius of the geostationary satellite where the mass of the Earth is 6 times 10 to the 24 kilos. So we can compare the centripetal force, which is mv squared over r, the gravitational force which is gm m over r squared, ignoring the negative sign. So m and m will get cancelled, r and r gets cancelled. We know that v is equal to 2 pi r over t. So if you incorporate that, we end up getting 2 pi r over t whole squared is equal to gm over r, which then enables us to get r cubed as gm over 4 pi squared times by t squared, which is Kepler's third law. And we just have to pop in the numbers, which are 6.67 times 10 to the minus 11 times the mass of the Earth as that, times by the orbital time period to be converted into seconds. So times it by 3600, square that all over the 4 pi squared. And then once we've got that, we cube root the answer. And I'm just going to put that under a cube root. And that will give me 4.2 times 10 to the 7 meters. Part B. A satellite of mass m is in a circular orbit around a planet of mass capital M. The radius of the orbit from the center of the planet is r. The gravitational potential Vg at a point, a distance r from the center of the planet, is given by this equation. By considering the cause of the centripetal force on the satellite, show that the kinetic energy of the satellite is equal to half the magnitude of its gravitational potential energy. So we know that gravitational potential energy is minus gm m over r. Now we can ignore the negative sign because it's just talking about the magnitude only. And we know that kinetic energy, generally speaking, is half mv squared. Now, knowing that v is gm over r, now that can be obtained using, so that's just already squared form. Now that is simply by using the equation above, where you have v squared equal to gm over r. So just using it from there, we can say that this bit over here represents the gravitational potential energy, and therefore kinetic energy is half of it. It's as simple as analyzing the two equations, two formulae, and that's basically the answer. Okay, let's move on to part II, where it says a tiny satellite of mass 1 kilo is to be launched from rest from the surface of the Earth into a low Earth orbit. Gravitational potential at any point in this orbit is minus 56 megajoules per kilos, and the value of the gravitational potential at the surface, at the Earth's surface, is minus 63 megajoules per kilos. Show that the satellite must gain more than 30 megajoules of total energy to achieve and remain in this orbit. Okay, so imagine that you have the Earth over here, and at the surface of Earth we have a gravitational potential of minus 63 mg per kilos. Okay, and then it is moved into an orbit where the gravitational potential is minus 56. If we look at the difference between the two numbers, it is simply 7 megajoules per kilos. Okay, and then we look at the total energy, and we know, so total energy is equal to the gravitational potential energy and the kinetic energy. Kinetic energy is half the gravitational potential energy. So kinetic energy being halved, of 56, okay, that is going to be 28 megajoules. I'm ignoring the fact that it's in megajoules per kilos because the mass is obviously 1 kilo, so you times it by 1, you just get the same number. So that's 28 megajoules. And so if we look at the two numbers over here, which is 28 plus 7, we end up getting 35 megajoules of energy. So that is more than 30. So that is part II done. Let's move on to part C. Large satellites are often launched by rockets from sites near the equator. The rotation of the Earth increases the initial kinetic energy of the rocket and the satellite. A new strategy is to launch using a smaller rocket from a high-flying aircraft. Use the information in part BII and the data below. Evaluate the advantages and limitations of this strategy. Use calculations to support your evaluation. We've been given a bunch of numbers. The rotational speed at the equator is 460 meters per second. Now this will provide an initial kinetic energy. And so initial kinetic energy of mass of, for a mass of 1 kilo of a satellite is just going to be half times 1 times 460 squared, which gives me 10,105,800 joules of energy. Let's look at the other table where it says that the operating altitude is 10,000 meters and the aircraft cruise velocity is 230 meters per second. So first of all, let's talk about 10,000 meters. If that's the gaining altitude, the potential, the gravitational potential energy for 1 kilo of an object is 1 times 9.81 times 10,000, which gives me a value of 98,100 joules of energy. And we are given the cruise velocity, which then helps us work out the kinetic energy as well. So kinetic energy again will be half times 1 times 230 squared, which gives me a value fairly large, and the total energy therefore will be the sum of the two, which is 124,550 joules. Okay, so let's just talk about in terms of part BII, where it was 35 megajoules of energy. That's the total energy. If we compare the initial kinetic energy, that is roughly about 0.3% of the total required. And if we compare the total energy over here to the one in part BII, we end up getting about 0.4% of the total. Okay, so that's gonna form a lot of marks in my 6 marker here. So in terms of the advantages, I'd say that the aircraft method provides more initial total energy, so less fuel will be needed. And this method isn't restricted to launch site limitations compared to equatorial launches. But in terms of the limitations, the problem is with larger satellites. The larger satellites from the equatorial launches will increase the kinetic energy of the satellites. So for aircraft-only launches, to still be efficient, we can only use smaller satellites. One other limitation is that both methods only provide a very small additional energy compared to what's actually required, as seen by these numbers of just 0.3% and 0.4%. Question number 23. The diagram shows some of the energy levels of the electron in a hydrogen atom. An electron moves from energy level X to Y. We need to show that the wavelength of the photon produced is about 410 nanometers. So we know that the energy gap is equal to the energy of the photon. So if you have an electron over here going down, then it just means that a photon would be released. And that is hf, the energy of the photon, which can also be modified as hc over lambda. So if you want to work out lambda, we just have to divide hc over the change in energy, and that's pretty straightforward. So 6.63 times 10 to the minus 34 times by the speed of light and divided by the energy gap, which is nicely given in joules, and that would be from minus 0.58 to 5.42 times 10 to the minus 19 joules, and that gives me a value of 4.11 times 10 to the minus 7 meters. And if you want to convert it into nanometers, you just have to divide it by 10 to the minus 9, and it will give you 410 nanometers. So for part B, the light from the satellite in a distant galaxy is analyzed on the Earth using a diffraction grating. The dark lines are observed in the spectrum, and an astronomer concludes that the dark line at a wavelength of 432 nanometers corresponds to the electron transition between X and Y. Explain the origin of the dark lines. Dark lines are due to the absorption of specific photons, which have energy of hc over lambda, as the electrons get excited and jump up. And it's caused by the light that's passing through the cooler stellar atmospheres. Calculate the recession velocity v of the galaxy. V over c is equal to change in wavelength over change the original wavelength. Therefore, v is equal to the change in wavelength, which is 432 minus 411 times the speed of light divided by the original wavelength of 411. No need to convert this into meters as it's proportional, and so once calculated you'd get 1.6 times 10 to the 7 meters per second. And for the last part, it says, state the name of the theory that is supported by the evidence from the measurement of the recession velocities of galaxies in the universe. That's expanding universe. Okay, that's the end of the paper. I hope you found this useful. Any questions, please leave comments below, and I will see you next time in the next video. Thanks ever so much for watching.